So in the previous lecture, we have seen some general information about the aircraft's operation field, which is called the aviation complex, the definition of an airplane, how it is different from other types of flying vehicles in terms that it's used, the aerodynamic flight principle. We have seen what is basically aerodynamics and some aerodynamic variables like the pressure, its definition, and so on. And we have a little bit touched the tip of the iceberg about the functioning of the aircraft in the big picture, which is called the life cycle of the aircraft, the cost of the life cycle, and some very general definitions. Now we get a little bit into some closer details onto the aircraft units working in flight itself. So now we have to focus on the aircraft working in level flight and see the forces that are acting on aircraft in flight, and how these forces govern the movements of the aircraft in flight, and how to balance them between each other to ensure a level flight, and also to ensure an efficient flying characteristics of an aircraft. We'll also explore some concepts of the G-force and its impacts on the structural standards used to evaluate the aircraft's suitability to operation, what is called airworthiness. Airworthiness means that if the aircraft is airworthy, that means that it's has the green light to take off. It's allowed to be operated based on certain types of tests. We're going to see which tests are required to ensure that the aircraft is able to fly. And then we'll get through some different aerodynamic configurations and explain how they work. So an aerodynamic configuration is basically the mutual position of the wing and for example, the vertical tail and other control surfaces, and how this mutual position is needed to imply a certain balance scheme about the aircraft's aerodynamic forces, so that the aircraft again can fly stably. So it can fly it's a level flight, for example, with a constant speed, with a constant velocity, and also so that we have the possibility to govern the aircraft's motion in space. So if we want, for example, to change aircraft's speed or altitude or direction, so if the aircraft wants to follow a certain path in space, then these notions of the aerodynamic configuration is very important in terms of how to generate those forces which are needed to govern the aircraft's motion in space. So now we can start shortly. This is basically a common picture of forces acting on aircraft. This is not a level flight. This is in fact an aircraft that is flying at a certain angle of attack. So as you can see, the nose is a little bit raised. So this is, for example, an aircraft that is gaining altitude. So it's not a level flight. And we're going to see the difference between, for example, flight in a level flight and flying in, for example, certain path that is not level when the speed and the altitude do change over time, right? So basically, this picture is just for demonstrating the main forces that are acting on an aircraft in flight in general, in a very general way. So these are the total forces, because, for example, the lift, the drag, the thrust, the weight of the aircraft is distributed along the entire surface of the aircraft. It's not basically in a certain point like it is shown here. But we can, for example, assume that the mass force is applied in the center of mass, which is, for example, W force here, the weight of the aircraft. So this is a model, if you like. So this is the physical model of an aircraft in flight. And here, if we can see the origins of these forces and where they come from, then we can understand how to manage these forces so that they're going to be beneficial for the aircraft's motion, either in a level flight or in this case, for example, a flight with gaining altitude or some other types of maneuvers. So we can start with the first. So the first force here, which is the weight of the aircraft, its source is basically obvious. It is the gravity field, because wherever we have something that has a mass, and the aircraft here has a mass, then it will immediately fall into the grasp of gravity. And this force, the W force here, is proportional to the mass and also to the gravity. So it is the mass multiplied by the gravity. So it's according to Newton's gravity concept. So the source here is pretty much clear. You can study in the courses of, for example, fundamental physics about, so you can get some details about why the gravity happens on and how it acts and how it works and so on. So here for now, for us, we can just take note that this is our enemy, number one, because we need to overcome it. And to do so, we have to generate lift. And to do so, we have to push the aircraft at a certain speed. Why? Because it uses an aerodynamic flight principle, right? So an aerodynamic flight principle implies dynamics, right? And dynamic means motion, it means movement. It means something that changes over time. and if the position of the aircraft changes over time, its speed, so it has to develop a certain speed so that to generate lift, so that to overcome the gravity force. And in this regard, we have another force which is required to do so, which is required to get dynamic part of the flight principle, which is the speed, and this is the thrust force, the T force, right? So here, the source is also pretty much straightforward, clear. There have to be an engine that is pushing the aircraft forward, right? And this engine works is obviously clear. It uses the energy stored on board on the fuel, which is the chemical energy, which is kind of a potential energy of the fuel, and it is chemical energy. And then this energy is used by the engine, transformed into a mechanical energy in order to generate the thrust, right? So it's moving the engine, and the engine is sucking the air and then pushing the air from the exhaust, and this is how the thrust is generated, right? So there are also other details that you're going to study a little bit later. But for now, we need an engine in order to generate this force, in order to push the aircraft forward, in order to generate lifts, right? So we can understand the reason and cause relationship between the engine and why it is needed for generating, for having aerodynamic flight principle in first hand. And by now we can understand two things, that the weight of the aircraft is our enemy, so it has to be as minimum as possible, because the smaller the weight of the aircraft, the smaller the lift is required, and the smaller the thrust is required also to push the aircraft at a certain speed, right? So the less the speed is required in order to take off, right? So this is just a very simple note that we can understand for now. And also we can understand that the price or the cost of flight is this force, is the T force, which is here generated by the engine, and the engine uses the fuel. So it burns the fuel, and the fuel costs money. So this is basically the cost of flight is coming from this force, right? So the smaller the force required to take to get the aircraft airborne, to keep it airborne, to at certain speed, to generate certain speed, to generate certain thrust, the smaller this force, the cheaper it is to operate the aircrafts, and in fact, the more some other characteristics of the aircraft we're going to see shortly. And the last force that is remaining here is the drag, right? It's also an aerodynamic force similar to the lift, right? So here the source is the aircraft's motion in the air, which is a gas, right? And the interaction of the objects in the gas, which is part of the aerodynamics as a discipline that studies the motion of objects in gases and other fluids. So the lift and the drag sources is the air, right? So this is why they're called aerodynamic forces. And in fact, the air and its interaction with objects, it's quite a very complex object to study. And here there are certain sources of the lift itself which are going to be different than the drag, although they are both aerodynamic. Then we can see, for example, these basic two sources of aerodynamic forces in terms of the physics of airflow, right? So when the airflow flows a certain objects, the pressure distribution is going to generate aerodynamic forces, right? So for example, coming back to here, the lift is generated because there is a difference in pressure between the beneath the wing and the upper parts of the wing, right? So the pressure distribution is clearly a source of an aerodynamic force, which is in this case the lift, and also in fact a little bit the drag. We're going to see all the details about the drag here, which is a little bit more complex in terms of the origins and the sources. And the second source is the shear stress distribution. It's a little bit not very clear, and that's why it's going to take a little some effort to explain how the shear stress distribution and what is the shear stress, in fact, by itself as definition. For now, we can just say that it's because of the viscosity of the air, right? So if the first item here, which is the pressure distribution, has to do with the fluid exerting a certain force on the object itself, on the surface, as we have seen the definition from the last lecture, it is a force that is applied to a certain point to every point, in fact, wherever we have a gas or another fluid. Why? Because the particles of the gas are moving randomly, and they are occasionally cross every single point in space where we have the gas, right? So at every point of space, we have a value of the pressure, which shows how much force it is exerted on the surface in this very point, right? In this exactly this point. So, and if we sum up all of the points of the aircraft, for example, here, and we see the difference that they're going to be, for example, the pressure that is exerted on a certain point is going to be more or less, and the pressure distribution is going to result in a certain force, right? Now, to the second point, the shear stress distribution, it is because the air, just like other types of fluids, and by fluid we mean a gas or a liquid, right? So, and they're both collectively known as fluid because they have something similar which is the interaction, the intermolecular interaction is different than a solid, right? So if a solid, for example, it has a certain shape in space, so it is difficult to deform it. So in order to deform it, you need to apply, for example, certain force on this subject, and it is to be constrained. So this is part of the structural lectures. The fluids, like the gases or the liquids, they are different in that their intermolecular forces are so small that the molecules, they move somewhat freely in space, especially for a gas where the movement is completely random, and that's why the gas basically doesn't have any kind of shape, right? While the liquid, it may have a shape of the bottle or of the capacity that is moved inside of it. For example, if you put a glass of water, then the water is going to take the shape of that cup or some other kind of capacity that is put in. While the gas, it doesn't have basically any shape. It cannot have a shape because its particles are not interconnected with each other, and to that way that they can move randomly. However, they still have some relationship. They still have some forces inside of the molecules of the gas, which causes the viscosity, right? So it is not entirely an ideal gas, what is called in physics. An ideal gas means that there is completely no forces inside between the molecules of the gas, so the gas is moving completely freely and generating only pressure, right? So the only force is generating pressure if it is an ideal gas, right? But because the real gases like the air is not ideal, it's more like a liquid. So sometimes it behaves a little bit like liquids, like water, and it has something called viscosity, right? So it is a little bit viscous, right? Although the viscosity, for example, of air is much smaller, is many times, probably 100 times smaller than other liquids like water, right? And water is, for example, if we compare viscosity, water is not a very viscous liquid. It's not a very thick liquid like, for example, honey. So honey is much more thicker and much more viscous as compared, for example, to water, right? So, but nonetheless, this term, the viscosity term, talks about how a certain layer of the fluid is linked to other layers, right? So, for example, if this aircraft is moving through the air, right? The immediate layer, which is called the boundary layer on the surface of the aircraft, it gets a little bit stopped by the friction of the surface, right? Because the surface is not ideally clean, or let's say, for example, it has a certain type of friction drag, right? So, and because of that friction, a certain layer, which is the boundary layer, it stops moving on the aircraft. And when this boundary layer stops moving, it impacts the upper layer, which a little bit loses its energy, and the upper layer also loses energy because the lower layers also have lost the energy. And this is what is known as friction drag, right? So the shear stress distribution is was the reason why we have a friction drag, right? And the pressure distribution is what causes the other forces of the lift, for example, and also, in fact, a certain part of the drag, which is called the pressure drag. We're going to come to the details gradually. All right, so again, to conclude this point, from physics of airflow point of view, we have only two sources of aerodynamic forces. So we may have a very large field of forces that are acting on an airplane, for example, which is, for example, we have some forces that's coming from the tail, from the wind, from the engine, and so on. But everything that has to do with air, it can be only two things, right? So it can be only a pressure distribution or a shear stress distribution. A pressure, again, it is the molecules pushing against somebody, and the shear stress distribution, it is the viscosity. It's because the air has some thickness, has some viscosity. That's why it creates the friction drag, right? Now we can move on slowly. This is the picture of the pressure distribution around an airfoil, and it shows why we have, for example, the drag, right? So it explains the first point, why, for example, the pressure distribution causes, for instance, the lift and the drag forces, and how to generate lift and how to overcome the drag in this regard. So from this picture, we can see, for example, certain regions where we have high pressure, where the object, which is here, the wing airfoil. So this is a section about the wing airfoil of an airliner. So it is quite an efficient airfoil in terms of generating lift, because airliners need to be quite efficient to be fuel efficient. So it doesn't have quite a lot of drag, and it has quite a large amount of lift. So it is quite a very efficient, so good airfoil. Right, so here what we can see is a very large red region just at the nose of the airfoil, right? So this large region means that the fluid, which is the air, is pushing against the airfoil at very large forces, right? Because the pressure there is very high. There is an accumulation of particles there that are hitting the nose of the airfoil, right? While if we move a little bit along the chord, which is called, so the chord is this dent of the airfoil, what we call in aviation the chord. So if we move along the chord of this airfoil, we can see some blue regions, which means that there the pressure is very low, which means that at this point, which is above, for example, the airfoil surface, the particles are not pushing the airfoil as much as they do, for example, on the nose or on some other locations. Now, we have to understand why there is difference, for example, regions of pressure where we have high pressure and low pressure. So what is the reason? What is the cause? What is the origin of this force? Now, it is clear that it is the motion of the object, right? Because the object is moving in the air to a certain speed. The result is this picture, right? And now, if this object was not moving, for example, if it was static, then we will have something known as the static pressure, right? So the static pressure is, for example, right now I'm not moving in space, so I'm experiencing a certain pressure, which is basically 1 atmosphere. So 1 atmosphere is about 12 kilograms per centimeter square. So it's quite a very large force indeed, right? So you might ask how, for example, things don't get squashed by such a large force, which is 12 kilograms on every centimeter square, right? So it's a very large force. And the reason why the things don't get squashed is because it happens equally from every side of the object, right? So for example, now on my hand, I have this force, which is 12 kilograms per centimeter square from this side and also from the other side, right? So my hand doesn't feel any force to be pushed on either side. Why? Because the pressure is again similar at every point. However, if I start, for example, moving at a certain speed, if I start moving my hand, for example, at a certain speed, and for example, in order to generate lift enough to take off for this aircraft, it's about 300 kilometers per hour, right? So it's a very large force. It's a very large velocity of the air itself, and it's a very large velocity of the aircraft, right? So now, when the object starts moving at a certain speed, when it starts developing certain velocity or certain dynamic, the air dynamic. Why do we have the aerodynamic forces onset? It's because the object is now exerting pressure on the gas, right? So the gas is otherwise static. It has a static pressure, which is equal everywhere. And now when the object starts moving, now it is the object that is pushing against the air, right? So it is the pressure that is exerted by the objects on the air, not the opposite, right? But what the airfoil feels, it feels this picture, right? So it feels a lot of pressure on its leading edge, right? Why? Because it's the leading edge attacking the gas, right? So the leading edge is attacking the gas at a certain speed, which may be very large. So in fact, this picture here is at a very large, Mach numbers, very large speed in order to have that large amount of pressure, which is written here in pascals. You can see the legend there. So again, when we have motion of the air or motion of the objects against the air, so it doesn't matter whether the object is stable and we are, for example, accelerating the air, like in the wind tunnel, or there is a wind load on the object, or the opposite, or the air is static and the object is taken off, for example, the object itself is moving. So we have certain parts of this object which are pushing against the air, right, and therefore increasing the pressure at those very locations, which is the leading edge in this case, right? And now this large pressure on the leading edge of the airfoil is generating drag, right? Why? Because it is preventing the aircraft's motion in forward, right? So it is preventing, dragging the aircraft backward, right? So the engine is pushing to push the aircraft forward, while this force on the leading edge of the airfoil, in this case, which is a very large pressure, it is pushing the aircraft on the other direction, right? So it is preventing the aircraft from moving forward, and therefore it is drag, right? And it is not a very good force for the case of generating or case of flight, because it is directly, in order to overcome this force, we need to have the thrust, which requires fuel to be burnt, which takes quite a lot of money, right? So it is costs. So this drag, this pressure drag, which is on the leading edge, is costing us quite a lot of money, and therefore we have to reduce. We have to make the airfoil a little bit more streamlined in order to reduce this force, right? Now, moving a little bit swiftly on. Just after the leading edge of the airfoil, we have a very low pressure on the top surface of the airfoil. And why this low pressure has occurred here, it is because of the acceleration of flow, right? So here we have another variable, which is called the velocity of flow. So it's called the speed of the air and how it is moving. Now, because the accumulation of the particles on the leading edge of the airfoil, it creates kind of a potential energy. It's like a pressurized gas, right? It's like a pressurized balloon. If we take, for example, a balloon and you create a lot of pressure inside of this balloon, and then if you remove, for example, the clump, then this gas is going to be accelerated in all other directions. And the same thing happens here, right? So although this is drag, so the high pressure on the leading edge of the airfoil, although it is a bad force, it leads to accelerating the flow on the top of the surface of the airfoil. And when the flow accelerates, those particles, instead of bombarding the surface of the wind, they start having another direction of flight, right? So they started kind of moving away from the wind, right? And therefore, their pressure decreases dramatically, right? And therefore, the difference of pressure is created, and therefore, we have the lift force, right? So again, because of the acceleration of the flow, we have reduced pressure, right? And this is called the Bernoulli law, by the way. The Bernoulli law, or the Bernoulli equation, it links this variable, the pressure, with the velocity, right? And the Bernoulli law says that with increasing the velocity, the pressure drops, and the opposite is true. And the opposite, in fact, happens on the leading edge, because the leading edge, the air particles stop, so their velocity is reduced, and therefore their pressure is increased, right? So the opposite relationship, or the relationship between the velocity and the pressure, which is an opposite relationship, when the velocity stops or when the velocity drops, the pressure rises, right? And the opposite happens on the top surface of this wind, where we have an acceleration of the flow and therefore a reduced pressure, right? And the result of this pressure field, or this pressure distribution, which is here the first source of aerodynamic forces, leads to two things now, right? So we have the lift, which is the difference in pressure between the top surface and beneath the wind, and the drag, which is the difference in pressure between the leading edge and the trailing edge, right? And there are in fact some other sources that we're going to see also here. Now this is the three-dimensional picture, and here also we can see the regions of low pressure above the wind, and we can see also the nose of the airfoil is red, the nose of the fuselage is red, for instance, which means there is a high drag there, which means that the fuselage is attacking the gas, and therefore the particles accumulate just at the nose, preventing its motion forward and therefore generating drag. And also we can see that the leading edge of the airfoil of the engine nacelle is also red, which means also drag. And we can see that the top surface of the wing is blue, which means very low pressure, which means there is a very large amount of lift that is generated there, right? And we can see some other things here. For example, the wingtip vortex, it is the tip where the wind ends. There is a wingtip vortex, so there is a vortex motion of the gas there. And inside of the vortex, if you look closely, you can see that it is blue, right? And that means there is low pressure now beneath the wing, which is a drag, right? Because the aircraft wants to move forward, and this vortex, which has low pressure in its core, it is preventing the aircraft, so it is sucking the aircraft from backward, right? So now it is also a drag, right? And the total force of lift and the total force of drag is the integration of all of these pressure field, right? So if we integrate, if we sum up all of the pressures, high pressures and the low pressures along the entire surface of the aircraft at certain direction, at certain axis, we can find two things: certain forces which are going to be lift and certain forces which are going to be drag. And their relationship, which is called the lift-drag ratio, is a central part of aircraft design, right? So the more lift we have, the better, and the low drag we have, the better. And that means the higher the lift-to-drag ratio, then that means the better the aircraft is going to have in terms of aerodynamic characteristics, right, or flight performance. Now, talking a little bit about the second source of the aerodynamic forces, which is the shear stress distribution. So here, as I've been said in the beginning, the shear stress distribution causes friction drag, right? And this is a very famous experiment to demonstrate or to explain what is a friction drag and how it onsets, and the notion of the boundary layer, right? So which is what can be seen here. It's in fact a very small region just on the surface of the object. And this is in fact a flat plate, just to exclude the pressure distribution, to understand only the shear stress distribution. So here we can see that on the surface of the plate itself, the air, or the motion of the air, or the motion of the gas stops, right? So it means that these vectors are the velocity vectors, right? So the smaller the vector, the smaller is the velocity, and you can see that on the surface itself, the velocity is 0, which means that on the velocity itself, on the surface itself, the gas stops moving, right? And why it is the case? Because this is a solid object, and it has certain value of resistance to moving the gas, right? And this resistance leads to stopping the motion of the gas, right? And no matter how fast this gas is moving on the surface itself, they're always going to be a zero velocity, right? And this is because of the viscosity of the fluid, right? And this is a real experiment in wind tunnel visualization. Again, this is a very small layer on the flat plate itself, so it can be only a few tens of millimeters, right? So it's only 0.1 millimeter or even smaller than that, like 0.01, depending on the speed, depending on the object itself, the size of the object itself. So this plate is clearly very thin, right? And when the gas moves, you can see that on the plate itself, the gas stops. That's what is visualized by the smoke. The smoke shows that the gas stops, and because it stops, the upper layers, they also lose energy, right? So as you can see, the vector, which is just adjacent to the surface itself, is a little bit smaller, and the upper vector is a little bit also smaller. And you can see the difference between, for example, the velocity before the plate, which was without the shear stress or without the friction drag, and the difference when the gas encounters the surface of this plate, where the gas stops just immediately on the surface, and this leads to what is called a friction drag, right, or what is called a shear stress distribution. And if we talk about an aircraft, for example, like this one, then here all of this surface is experiencing indeed a friction drag. So the surface of the fuselage, the surface of the wing, the engines, and the pinion that is used for holding the engine, for example, what is called the belly fairing beneath the fuselage where the wing is attached, the tail, all of these objects, because they have kind of something that called wash surface, because they have kind of surface that is washed by the gas. So when the gas washes or passes through this surface, is going to generate inevitably a large amount of drag, which is called the friction drag, right? So now this is different from the pressure. It doesn't matter what is the shape of the objects, right? So it doesn't matter whether it's streamlined or it's not streamlined. If we have a certain surface that is washed by the gas, inevitably we're going to have this picture on the surface of the gas, on the surface of the objects. And so on the surface of the object, the gas stops, and the upper layer loses energy, and the upper layer also loses a little bit of energy until we go a little bit far away from the surface, so that the is going to be moving at full speed. And the closer we get to the surface, the smaller it is the speed, and the more it is going to be the resistance of motion in this gas. And again, why it is the case? It is because of the viscosity of the fluid, where a certain layer, if it stops, then the upper layer, because of the intermolecular forces inside of the gas, prevents the upper layer from motion, and the upper layer is also linked to the lower layer, and the upper layer is also linked, and this is why the layers stop each other gradually, and until we move really far away from the surface itself, right? So that's the source of the shear stress, and that's the source of friction drag. So this is called the boundary layer, right? So this is the layer that is just adjacent to the surface itself. Again, it's very small. It can be like 0.1 millimeter, for instance. And coming back to the wing, so this is how this boundary layer, in fact, looks like, right? So this can be it can have different shapes depending on the location on the airfoil. And here we can see how it shifts along the airfoil, and it's the amount of the friction drag that is generated because of this boundary layer. It's different at each part of the airfoil, and that's why, in fact, when we talk about the source of the aerodynamic force, we say the shear stress distribution, right? So it is different again at every point in the object, right? And depending on the amount of the friction that is generated at certain locations and other locations, if we sum this up, if we integrate all of this distribution along the surface, we're going to find the total amount of friction drag that is generated by, for example, this object, right? This is the same picture now obtained by computer simulations, which is called the CFD, the computational fluid dynamics of, for example, this is an airliner wing that has this kind of high-level devices, which is the leading edge device, which is called the slat, and the trailing edge device, which is called the flap. So because of the interrelation between the slots, the main wing and the flap, so the boundary layer shape, as can be seen in zoomed picture there, changes its shape, right? So you can see, for example, it's in the beginning, it's a little bit like here, right? So this is called the laminar boundary layer. So it is just a very simple relationship where the velocity increases the far away we move from the surface. And if we move at certain other locations on the airfoil, we can see that that relationship is a little bit changed, where we have the gas completely stops on the surface, and the picture of the boundary layer changes, and this impacts the friction drag, right? Now we can see that unfortunately we don't have the legend that talks about the size, but indeed you can see how we can zoom. We are zooming, in fact, in the nose of the airfoil. So this is the blue low color on low pressure on the nose of the airfoil. It is zoomed on the upper part here, and itself it is zoomed a little bit below. So it is very tiny layer on the surface of the wing, right? So it is like 0.01 millimeter or even smaller than that, right? So this tiny layer is what is causing the friction drag, which is a very large force if we integrate the entire surface of the aircraft, which can be, for example, a few tens of meters square. So it's quite a very large force. And this is in fact the same picture that we have seen here, but on the surface, right? So here we're seeing on the section plane, we have made a section on the wing, and now we're looking at the wing from the top, and we can see the boundary layer states at different locations on the airfoil, and in fact we can see where the friction drag is taking place the most of all. For example, beneath. Just downstream the engine, because of the interference between the engine and the wing, we have this kind of trailing edge, which means that the gas there is experiencing some very large friction. That's why it stops, and when it stops, the oil accumulates, and when it accumulates, it becomes more lighter, right? So regions with lighter oil, this means that those regions are experiencing low velocity, right? So because if the higher the velocity, the oil is going to be moved away from the surface of the aircraft, and in this case, we're not going to see the bright colors which are seen there. And the brighter the location, the lower the velocity, right? So it is a very good visualization of the velocity field. So we can see at every point of the wing how much is the velocity. And by looking at this picture, we can understand where we have large friction in this case, because if the velocity stops, if the oil is brighter, that means at those locations we have a large friction drag, and we have to do something about that to reduce the drag of the aircraft. And this is why we need this kind of experiment where we can visualize, so we can see the regions that are generating a lot of drag, and we have to kind of heal those regions so that we can reduce the drag. This is also a picture of an aircraft in a wind tunnel. Here also we can see the regions where, for example, we have flow separation, like, for example, the tip of the wind, as you can see, because now this is kind of something different than the friction drag. It has to do with separation, where, for example, high angles of attack, the air is not attached to the surface anymore, and that's why there is no motion of the air there, and that's why, in fact, for example, you can see the tip of the wing, it becomes partially black, and that means that there is no air there. That means there's flow separation, and that means that there is no lift generated there, right? So because for lift to happen, so in order to have this kind of blue low pressure on the top surface, there have to be an attached flow, right? So the air needs to be attached on the surface, to the surface of the aircraft. And when the aircraft raises its nose very high, or if the aircraft velocity is not enough, then the air becomes detached from the wind surface and it's not generating lift anymore, right? So this is what happened in this case, for example, at the wingtip at very high angles of attack, right? So when the aircraft raises its nose very high, the air becomes detached, and therefore there's no lift, and the aircraft basically starts to falling down. This is the same picture now obtained also from computer simulations, also CFD. So it shows also the regions where we have high friction, low friction. And we can sum up a little bit what have been learned here from the source of the aerodynamic drag. So we have the pressure drag, the parasite drag, and the interference drag. And the pressure drag itself, it has to do with the airfoil drag, the induced drag, and the wave drag, right? Now, so if we integrate, here the lift force has only one source, which is the pressure, right? So the difference in pressure generates lift, right? And there is no other source of lift otherwise. While the drag, as you can see, it has quite a lot of sources. At least we have, as we have learned from, for example, the boundary layer states and other forces, at least we have two things. At least we have the pressure, which is, for example, the leading edge, the high pressure at the leading edge, which is preventing the airfoil from moving forward. And you have also the shear stress distribution. You have the boundary layer, which is also kind of friction, which is also preventing the aircraft from moving forward. And therefore, we have at least these two things, right? From our discussion, we have at least the pressure of the airfoil, and we have also the skin friction, which is called the parasite drag, right? Now, there are some other sources as well of the drag, which are have to do either with the pressure or with the shear stress distribution. And basically, apart from the skin friction, all of these have to do exactly with the pressure, right? So, for example, the induced drag, it has to do with this wind tip vortex at the three-dimensional, because the wind has a finite span, and at the tip of the wind, the high pressure meets the low pressure, and this generates this kind of vortex. And because we have a vortex, the flow is accelerating at certain points around this vortex at the core, and because of the acceleration of flow, according to Bernoulli law, we have low pressure, right? And low pressure in that core is like a rope that is preventing the aircraft motion from forward, and that's called induced drag. Why it is called induced drag? Because it has to do with the lift, right? When the lift induces the wind tip vortex, right? So the lift causes or induces the wind tip vortex, and the wind tip vortex causes less drag in its core, and less drag in its core causes drag, right? It prevents the aircraft motion from forward, and this is clearly visible from this picture. Behind the aircraft, we have the vortex, and we have the tip at the core. Inside the center of the vortex, we have a blue low pressure, right? And that means drag, right? So that's the second source here, which is called induced drag, right? So the pressure drag has to do with airfoil and induced drag. And lastly, here we have the wave drag, which has to do with the flying at very high speeds close to the speed of sound. We have something called the shock wave. I'm not going to get into a lot of details here. You will have a course of aerodynamics, and you can study this subject very well. And so for now, I can say just that because when we fly at close to the speed of sound, we have a barrier, which is called the shock wave. And that shock wave is also something that prevents the aircraft motion forward in a tremendous way, right? So the drag increases like 4 times, right? Just because of this shock wave, right? So it is called the wave drag. And finally, here we have the interference drag, the third point here. It has to do with the when the object has different parts, like the wing, the fuselage, and because this discontinuity in the geometry, right? So for example, we have the wing, and then the wing finishes, and therefore we have discontinuity in the geometry. And this discontinuity in the geometry is going to lead to discontinuity in the pressure field, for instance, right? So for example, if we look at this picture, we can see that where we have the fuselage, there is some blue low pressure on the fuselage, right? So where it comes from? In fact, it comes from the low pressure on the wing, right? So the wing impacts the pressure field of the fuselage, right? Now, why this is bad? It is because this part of the wing that is attached to the fuselage is not going to be generating lift as efficiently as it would be if there is nothing there, right? If it was just a clean wing, then in that case, the low pressure is going to have a maximum values possible, right? And because we have the fuselage, the high pressure, beneath the wing is going to be first transformed to the fuselage, and then the fuselage will have different pressure. It will have a high pressure beneath and a low pressure from the top. And this because we have the viscosity of the fluid, the air becomes moving from beneath the wing to the upper side of the wing, right? And this is known as, for example, the separation bubble, right? It's known as the interference drag that is inside of it, which is called the separation bubble, or it's called also the junction area flow beneath between the wing and the fuselage. So this motion of the air from beneath the fuselage to the upper side of the fuselage, because there is a difference in pressure, it causes the wind to be less efficient, right? And less efficient wind means that it's generating drag and it's not generating lift, and therefore we have something known as the interference drag, here. So again, to summarize, the sources of aerodynamic forces from the point of view of physical flow, we have two sources. We have the pressure distribution and the shear stress distribution. Now, if we talk about the lift force as an aerodynamic force, it has only one source, which is the pressure distribution, which is the difference in pressure between the beneath surface and the top surface, right? Now, if we talk about the drag, then we have all of these forces that are acting on the surface and that are generating, that's preventing the motion of the object forward, and that includes the pressure drag, which comes from 3 sources: the airfoil shape itself, so the leading edge of the airfoil, for example, and the induced drag, which has to do with the wingtip and also discontinuity in the geometry, and therefore the motion of the air from high pressure to low pressure, and that generates a lot of drag. And the wave drag, if you're flying at transonic or supersonic speeds. The parasite drag, which has to do with the viscosity of the fluid, because the fluid sticks to any surface, like for example the surface of the aircraft, and prevents its motion forward, right? So that has to do with the boundary layer. And finally, we have the interference drag, because we have different geometry, and discontinuity in the geometry will lead to discontinuity in the pressure field, and this is going to lead to the wing losing its efficiency, and it will be generating drag rather than generating lift, and that's why we have this type of drag. So that's basically it. All these are the sources of the aerodynamic forces, the lift and the drag, and other forces. That's why we have to have a thrust to overcome all of these guys, right? So this is why we need to have an engine that is generating quite a very large force, which is called the thrust, in order to push the aircraft against all of these odds that are preventing the aircraft from moving forward.